Okay, welcome to Let's Get to the Marks. I'm going through the OCR A-Level Chemistry A, June 2024, Synthesis and Analytical Techniques. Analytical Techniques is 2 hours and 15 minutes. This is the 2024 paper. So basically the organic chemistry paper. It's out of 100 marks. You got, what's that, 135 minutes, 2 hours, 15 minutes. The first section of 15 questions is going to be multiple choice. Only take a maximum of 20 minutes for this section. So what I suggest you do is you start a timer and you make sure that you only spend 20 minutes. And before you get to your final exam, you need to make sure that you've got it locked down so that you can do 15 multiple choice in 20 minutes. All right. What I suggest you do is pause the video at the start of each question, have a go at the question, and then unpause and watch my explanation. Okay, let's get on with it. You should spend a maximum of 20 minutes. Write your answer in the box provided. All organic compounds have covalent bonds. What is the electrostatic attraction in a covalent bond between? A shared pair of electrons in the nuclei of the bonded atoms. B, cations and delocalized electrons. C, oppositely charged ions. Or D, two molecules. Hopefully you know this one. You have your, I'm going to go through the explanation. So if you haven't had a go, make sure you do before I go through this. So you have your protons inside the nucleus of atoms, and that creates obviously a positive charge. The neutrons are not charged. And then you have your electrons. So it's the shared pair of electrons between the nuclei, and it's that negative and positive, that electrostatic attraction between those. Okay, so we're going for A here, shared pair of electrons and the nuclei of the bonded atoms. It's the electrostatic attraction between those. Okay, coolio. Hydrogen reacts much more readily with alkenes than with alkanes. Why is this? A, alkenes are polar molecules, whereas alkanes are not. All atoms in an alkane have a full outer shell of electrons. The bond enthalpy of the CC sigma bond is higher than that of the pi bond. The bond enthalpy of the CC sigma bond is lower than that of the pi bond. This one's quite difficult, and I wouldn't be surprised if quite a few students go for A. I'm going to go through the explanation, so have a go at it. Okay, I'm going to go through now. So, are they polar? No, they're not polar. They do, alkenes, have an electron-rich or dense area, which is the double bond, but we wouldn't describe it as polar. So it's not A. All atoms in an alkane have a full outer shell of electrons. Well, so do these here in this alkene. That is going to have a full outer shell of electrons. Group 4, yeah, you got pair there, pair there, pair there, pair there. So it's not that. It's nothing to do with that. The bond enthalpy of the CC sigma bond is higher than that of the pi bond. And what I'm going to show you here is actually a double bond has a higher mean bond enthalpy than a single bond. However, the sigma bond itself, which is one of these bonds, is a sigma bond and the other one is the pi bond. The sigma bond is stronger than the other. So if one of these is going to break, it's easier to break this pi bond on the double bond than it is to break the sigma bond there or the sigma bond there on the CC single bond, even though together that has a higher mean bond enthalpy to break both of those. But it's easy to just break the pi bond there and get that alkene to react. So the answer is C. Coolio. And that is that the sigma bond, the single bond, is stronger than the extra bond we get with the double bond. All right, let's move on. Oh, my days, is going to take so long if I go this slow. So I've got a couple more questions here for you. So what we're going to do here, guys, is a student investigates the rate of hydrolysis of different iodoalkanes using aqueous silver nitrate and ethanol. What color of the precipitate is seen? So, and then we have question 4. The structure of but1ene is shown below. We have carbon X and carbon Y. Which row has the correct shape around the carbon atoms labeled X and Y? So you've got to decide which type of molecular shape these guys have. All right, why don't you pause the video, have a go at these two questions on some scrap paper with a pen, and then I'll go through the answers. Or I'm going to go through the answers with the explanation. A student investigates the hydrolysis of different iodoalkanes using aqueous silver nitrate in ethanol. What color of precipitate is seen? So when you hydrolyze this bond, which is the iodoalkane bond that we're talking about here, you're going to release, when you snap that, you're going to release iodine. And essentially, what is the color of iodine? Or, well, what's actually going to happen is the iodide ions, because if we just look at iodine, we would go brown, right? It's going to be brown in solution. It's dissolved in ethanol, just like it is in aqueous. But the iodide ions that are released from here, they're going to react with the silver ions in the silver nitrate. And I'm sure you know what color this is. This is the solid precipitate you're going to get forming, and it is No, not C, not white. That's chlorine. It's going to be D, yellow. So there we go. So we're not really looking at iodine. They're going to form silver iodide. So we're going to get a yellow precipitate seen. And it does say what is the color of the precipitate, not the solution. Now, if they asked us what is the color of the solution seen, there would be a brown solution as the iodine dissolves in the ethanol. But then, of course, iodide ions are going to react with the silver like that. Okay, let's move on. The structure of butyne is shown below. Here we go. What is the shape around these? So what's the shape around X? Well, if we look at X, X is going to look like that. So this is what X looks like. That's X. And if you have a look there, there are essentially, you can count this double bond as one alone. That's going to be trigonal planar. You can see 120, 120, 120. That's going to make 360. So trigonal planar. So we can get rid of A and D. So it's going to be B or C. Now we're going to look at position Y, and position Y is kind of like going to have a hydrogen there. If we draw its display formula out, and there, that is actually going to be pyramidal. And how do I know it's going to be pyramidal? Well, it's got 4 bonds. There's 4 electrons in carbon. There's no lone pairs of electrons. So it is going to be pyramidal. So we're looking at, no, tetrahedral. Sorry, tetrahedral. Oh my good gosh. Yeah, tetrahedral is what I meant. So it's going to be like, you get the coup, right? You get that. It's got 4 bonds around it, 4 electrons in, it's a group 4 element, so 4 electrons in the outer shell, sharing with 4. So there's 4 bonded pairs of electrons. You're always going to be tetrahedral. So the answer here is B. B. Oh my days, I think I'm losing the plot. Right, let's go. Question 5. Ger Geraniol, shown below, is a component in many natural oils. Geraniol, I don't know how to say that, guys. I'm going to be honest with you. Which pair of reagents identifies both functional groups in geraniol? Right. What we're looking at here, what are the functional groups? Let's identify them. Well, we have an alkene, we've got the double bond, and we have an alcohol. So what can you use to identify an alkene? You should know that. And it's going to be bromine, right? We're going to identify the alkene by adding bromine across it. It's going to go orange to colorless. Don't know why I drew it in pink. Going to decolorize them. Get rid of that bad boy. Get rid of that bad boy. We're left with either bromine and 2,4-dinitrophenylhydrazine or bromine and acidified dichromate. Now, if you add acidified dichromate, it's going to go green to orange, and that's a primary alcohol. It's going to form an aldehyde, and then if you reflux it, you'll form a carboxylic acid. So we are going to go with C as our answer here. 2,4-dinitrophenylhydrazine is for your carbonyl group, which we don't have present there. That would help identify that. And yeah, aqueous silver nitrate in ethanol, Tollens reagent. Yeah, that would identify haloalkanes, halide ions, and Tollens reagent would identify an aldehyde. Let's move on. Oh my days. Can I clear all that? Yes, I can. Thank you, Bob. Right, let's go. Question 6. 4.3 grams of the alcohol C5H9OH MR86 is burned in oxygen. You can see here. Which volume of oxygen gas is needed in decimeters for the complete combustion of C5H9OH at room temperature and pressure? Grab your calculator, grab your pen, grab some paper, pause the video, have a go. Well, I'm going to go through the answers. So first up, let's just get with the program. They've given us the mass and we've got the MR. So we just want to do mass over MR times moles. And we're going to find out how many moles of alcohol we've got. So this is the first step, 4.30 divided by 86. And how many moles does that give us? That gives me 0.05 moles of alcohol. Now, that doesn't look like much of a naught. That looks like a 6. Oh, whatever. Right, we've got 0.05 of that. Now we know it's a 1 to 7 with the oxygen. So we're going to times that by 7. And that is going to give me 0.35 moles of oxygen needed. Now, that's moles of alcohol. And that is the moles of oxygen needed as the ratio is 1 to 7. Now, it didn't ask us for moles. It asked us for volume in decimeters. So I need to times this by 24 decimeters, which is the volume of any gas at room temperature and pressure. So times that by 24. And we get 8.4. And that is how many decimeters, bosh, are needed for the complete combustion of that pentanol. Awesome. Right, let's move on. Don't forget to take your time to close out or pause the video and hit the like for me. That would be massively helpful. 7. Which statement gives a valid scientific reason for global warming? Infrared radiation causes bonds in the CH4 molecules to vibrate more. Infrared radiation causes O2 molecules to vibrate more. Ultraviolet radiation causes bonds in the CO2 to vibrate more. Ultraviolet radiation causes bonds in the CFC molecules to break. So we've got that question there. You should be thinking about which one it could be. And then we've got this one down here, which says the CFC CCl2 F2 can cause the breakdown of ozone in the upper atmosphere. Which initiation step could occur with the ultraviolet radiation to catalyze this breakdown? So what I want you to do is pause the video and have a go at these two. All right, I'm going to go through the explanation. So when we go through this, I'm going to show you how you should be eliminating your answers, which is a multiple choice technique. So ultraviolet radiation is not to do with global warming. This is to do with the ozone layer. So ultraviolet radiation, not to do with global warming. Infrared is what we're dealing with global warming. And have you heard of oxygen being a greenhouse gas? Of course you haven't heard of oxygen being a greenhouse gas. It's not a greenhouse gas. We're looking at methane, carbon dioxide, water vapor. There are many other greenhouse gases, but methane is one of our more popular ones. And the reason is that the infrared radiation causes that the specific wavelength of the infrared radiation, whatever, causes the bonds in the CH4 to vibrate more. And that is what causes the global warming. So the answer is A. Now, with this one, there is a quick way to do this one as well. You see this CF bond? This is some seriously strong bond, and that doesn't break. So I want to get rid of anything with a fluorine-free radical. What kind of free radical are you going to release normally with ultraviolet radiation? You're normally going to release this chloride free radical because the Cl bond can be broken. The Ci can be and the Cbr can be, but not the Cf. So we're going to release this one. So we're going to just go straight to C because that has got the only one with a chlorine free radical. I don't know what that is, but that's not a chlorine free radical. So that one's incorrect. Yeah, let's go with C. And this one is totally incorrect too. Okay, let's zing on to the next question. Right, what are we doing here? Which compound is a secondary amide? Now, secondary amides, so why don't you pause the video, have a go at this one, see if you can scribble it down on paper. Okay, let me go through. What is an amide? Before we even talk about secondary amides, an amide is when you have a nitrogen atom attached to a carbonyl group. So we've got this C double O bond, and then we have this nitrogen attached here. Now, a primary amine has two hydrogens. A secondary amine has one hydrogen attached. And then a tertiary amine has no hydrogens attached. So you might say, what's in place of the hydrogen? Well, it's going to be like an R group. Now, that could be an alkyl group or something else. So that's a tertiary. It's got no hydrogens on the nitrogen. That's a secondary. You just got one hydrogen. And that is a primary with two hydrogens. So which of these is a secondary amide? So I'm looking for one with one hydrogen. So look, that's an H. That's an H. That is a primary amide. Get rid of you. Over here, you can see there's one H attached here. So I'm going to put a question mark there. We'll come back to that. And then here, there's one H attached here. So question mark. These two look like they could be secondary. And then we come here and it's NH2 again. So this is a primary. There's no tertiaries here. Okay. We have an issue here. If you went for B, B is incorrect too. So that's incorrect because that's a primary. B is incorrect because it's not actually an amide. Have a look where the carbonyl group is. There's actually a carbon. If you were to draw the display, there's a CH2 group in between. An amide is when the nitrogen is directly attached to the carbonyl group, the C with the double A coming off of it. So this is this one's not even an amide. So this one here is not an amide. And this one here is the correct answer. It's only got one hydrogen attached to the nitrogen that is attached to the carbonyl. Okay, let's zing on. 1.35 ethylamine gas, CH3, CH2, NH2 with an MR of 45. Immediately you see that, you should be thinking, right, I've got mass, I've got MR. This should trigger you to go bish, bash, bosh, mass over MR times moles, right? So this is good exam technique to be speeding through. Then you've got a volume, because you've been given 20 centimeters. Then you've got a conc, and that should make you think about going bish, bash, bosh, moles over conc times volume, which is another equation you need to know off by heart. That was some crusty labeling there. Okay, what's the question? What is the concentration of ethyl ammonium chloride in moles per decimeter? So we're after a concentration as well of ethyl ammonium chloride, which is this product here. We know the ratio is 1:1. Let's work out how many moles we've got of each of our reactants and work out if they're the same or if one is excess and one is limiting. So let's do, first of all, 1.35 grams over 45, got 0.03 moles. And that is ethylamine. Oh my days. So we've got 0.03 of ethylamine. Now that is reacting with 20 centimeters. Remember, we need to turn to decimeters. Volume is always in dm cubed. So I want to do 20 divided by 1,000 and then times the conc of 2.0. And that is going to get me 0.04 moles. And that is of hydrochloric acid, HCl. So actually, this is excess. So when you have one in excess, don't use that in your ratio for the ethyl ammonium chloride, the product, because actually some of that's left over. So I'm going to use this. As I know that all of that will be used up, this is the limiting reagent, which is this one, ethylamine, is the one that we can use to find out the maximum amount of ethyl ammonium chloride we can make. As it's 1 to 1, it's going to be 0.03 moles of ethyl ammonium chloride. Now I know I've got 0.03. It's asking me for the conc for C. So I've got N, I've got C. What's V? I'm going to do 0.03 divided by 20 centimeters. The volume, 20 centimeters is 0.0, yeah, 20 decimeters. So, and that, my friends, is going to be 1.5 mole dm minus 3. That is the answer. So we're going with C, folks. Wunderbar. That one took a little bit longer, but it wasn't too hard. Right, we're on to question 11. Which compound could have produced the IR spectrum below? So we've got transmittance and we've got the wave number along here. This is where we're going to have to use the data book. So let's check it out, check it out, check it out. What I see, that first peak was the COO bond. Our carboxylic acid is that broad peak. And then there was another broad peak there. That would be an alcohol or a phenol. So what we got? Oh, look, there's no nitrogen atoms, so it can't be amine. So we 100% know we have a carboxylic acid, so we can get rid of that bad boy because that's just an alcohol. How do we know we've got carboxylic acid? We've got that at 1750. We've got this broad one, and this broad one here, just before 3000, that is the OH on a carboxylic acid. That is not an alcohol OH. So that means that oh, that's an ester. We can get rid of C. So that means our only possible answer is B or D. However, we have this peak here, which is around 3,400. And I think that is going to have to be the hydroxy group there. Okay. Well, look, there's no other functional group attached there. So that has to be responsible for that. So that is going to be our answer. D, 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 D. Lovely. Let's move on. Right. We're nearly there, folks, for the multiple choice. 12. 1.6 diaminohexane reacts with hexanediol dichloride to form a polyamide and one other product. What is the product formed in this reaction? Right. Why don't you pause the video, have a go at this one in your head? Okay, this should be fairly easy because whenever these acyl chloride type things react, remember they've got this going on. What's going to happen in this situation is normally the chlorine is substituted, so you get chloride ion coming off, and then one of these hydrogens here is going to join on with that. You're going to get HCl formed normally. So normally with acyl chlorides, you're going to get hydrogen chloride formed. So I would just skip straight ahead and guess at that. You're definitely not going to get water, carbon monoxide coming off or ammonia coming off from any of these. So yeah, it's going to be HCl. And let's zing on. So some of these you can do real quick and then others take a little bit longer. Okay. A sample containing a mixture of 3 components, X, Y, Z, is analyzed using gas chromatography. The gas chromatogram below is obtained. The relative peaks of X, Y, and Z are included. So we've got X, Y, Z. So there's 3 things in this sample. Record a response, and then we have the time, and then the relative peak areas. X is 1, Y is 3.5, and Z is 5.5. Which statements are true? The peak for component X shows the mass of 1 mole. No, that is not going to be the mass of 1 mole, the peak of it. No. Incorrecto mango. Component Y stays in the column longer than component X. Let's have a look. Well, component Y, we can tell was slower to go through the column. It was slower to go through. So no, it wasn't as slow, was it? Yes. So component Y stays in the column for longer than component X. Oh, oh, yes. I can't even read. I'm comparing it to Z. Yes, Y is, look, component Y stays in the column longer. Yes, it took how many minutes? About 4 minutes, didn't like about 4 minutes to get out. Component X took just under 2 minutes to get through the column. So yes, component Y stays longer, probably because it has a higher mass, right? So that is correct. 2 is correct. Component Z consists of more than half of the sample. Well, look, 5.5 is bigger than 1 and than 4.5, which is so Z is bigger than X plus Y, which is S. So yes, 2 and 3 are correct. So we're going to go with C. God, I explained that badly. Never mind. There we go. 14. The structures of rewind. The structures of three compounds, 1, 2, and 3, are shown below. Which compounds would produce a carbon-13 NMR spectrum with two peaks? Is it 1? Is it 2? Is it 3? I suggest you pause the video, sketch these out on a scrap bit of paper, and try and write in your carbon atom environments and see how many environments each one has, and then you'll work out the answer. All right, I'm going to go through it. So it goes a little something like this. Right, all you've got to do is look at how many different carbon environments there are. If you wanted, you could draw this out because, of course, that's 1, 2, 3, 4. That is pachong, 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 paching, paching. This is but 1,3-diene, and so we can see that that is unique. No, it's not. We got an exact copy there. They're the same, and there we go. We got two environments in molecule number 1. So you've got this carbon here is going to be identical to this carbon here. It's symmetrical, so kind of easy peasy this one. Yes, there's two environments. Now let's look at this one. What we got? We got 1, 2, 3, 4. So we got butane 1,4-diol, and we can see again this carbon is going to be identical to this carbon here, and this carbon and this carbon have identical environments. So we got two different carbon-13 NMR peaks there. There's basically two different carbon environments. Now we might look at this and think, oh, it's going to be 2 as well, because we've got one carbon environment here, which is going to be identical to that carbon environment, symmetrical molecule again. And then we have this carbon environment here. I'm saying this is the second type of carbon environment. And those two are identical to each other. Look, they're both connected to 1 there, and they have the exact same environment. And so these two are the same. So we've got 4 of those and 2 of these two. So again, that looks at first glance like it's 2, but don't forget there is a methyl group. This is skeletal formula at the end here and here. So this third one actually has another carbon environment here and here. So that one has 3 carbon environments. So our answer is 2, 1 and 2 only, and that is B. Boom. Last one of the multiple choice, and then I'm going to go through the long answer questions as well. Okay, 15. Polymers such as polychloroethene shown below are difficult to dispose of. Okay, polychloroethene. Which statements are true about polychloroethene? It is photodegradable or biodegradable polymer. When incinerated, it produces toxic waste products which need to be removed. 3. It can be recycled and processed for use as an organic feedstock. Okay, so if it's going to be biodegradable, we are expecting to see starch, a little bit more information here. So I would be expecting to know whether it has starch granules inside it or anything like that, and it doesn't appear to. So I would say, because normally you need microorganisms to be biodegradable, and those microorganisms will break apart the starch, which will break the cross links and stuff in the polymers and help split those apart. But there are no starch granules to the best of my knowledge here. Then when incinerated, it produces toxic waste products which need to be removed. Well, when you burn anything with a chlorine atom, and this is whatever that is, yeah, anything you burn with a chlorine atom, chloroethene is known as vinyl. So any of these kind of polyvinyl, yeah, whatever, PVC, polyvinyl chloride, whatever, they are going to produce HCl, hydrogen chloride, when burnt. So what I would say is 2 is true. This is true. I'm going to go with this is false. We haven't been given enough information on that one. So I'm going to say that is true. It can be recycled and processed for use as an organic feedstock. Ooh. Well, if you can reverse this addition reaction and you can go back to having that, then yeah, that is an organic feedstock. You can go back to chloroethene. Then yeah, I think if you can go back to that, 2 and 3. My best answer here would be only 2 and 3. But I know for a fact that what the example did with this question is, regardless of whether you put A, B, C, or D, the example gave you the mark. And so what they kind of fluffed on this question by not giving enough information. So we definitely know that 2 is true. Possibly 3, but they needed to give a little bit more information because I don't think it's as straightforward to reverse that back to chloroethene. And whether it's photodegradable or biodegradable, I don't know if that is necessarily, I don't know whether you're supposed to know if it's photodegradable is on your specification. Biodegradable, you're going to need a starch granule. So my answer would be C, my best answer. But you'd have to, yeah, check the exact specification. But this question in the 2024 paper 2 for OCR Chemistry A level had an issue because on their mark scheme, they said they awarded the answer for any of the 4 answers because there wasn't enough information for people to make the judgment. All right. That's the end of the multiple choice. Don't forget, share with Kevin, hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on the next video. Okay, welcome to Let's Get to the Marks. Going through a quick A-level chemistry organic question. Yeah, let's get into it. Yeah, this question's about hydrocarbons. Structures of hydrocarbons A to E are shown below. Grab some pen. Grab some pen? Never heard of that. Grab some paper. Grab a pen. Why don't you watch me do the walkthrough? Pause the video at the start of each question, then unpause and have a go and watch my explanation. Yeah, you get the idea what I'm talking about, hopefully. Which hydrocarbons are unsaturated? So which of these are unsaturated? Now, you're probably going to need to put more than one letter down, and you're going to have to get all of the correct, you're going to have to get the correct letters to score the mark. Which hydrocarbons are alicylic? So which of these five are alicylic? Which hydrocarbons have the general formula CnH2n? And what is the systematic name of hydrocarbon C? So you need to name that one perfectly. And then for the last one, which is worth like 3 marks, I guess 2 or 3 marks, explain why hydrocarbon D is a Z stereoisomer. Why don't you grab your pen, grab some paper, press pause on the video, have a go at these now, and then unpause or watch me go through the explanation. All right, I'm going to go through it. Let's go. Which hydrocarbons are unsaturated? So we look at A. Can't see any double bonds. A only contains C bonds. So we're going to say only contains C bonds. So this is saturated. Okay. A is saturated, not unsaturated. Let's look at B. Straight away, we can identify it has a non-C bond. So we're going to put B down as one of our possible answers. C, okay, does C just contain C bonds? No, it's got this delocalized ring, and that is going to count for me as unsaturated. Delocalized. So it's got this delocalized ring, so we're going to go with C there. Oh, look, mix of colors. Which hydro... Oh, no, we haven't finished. We haven't reviewed D and E, and it's quite easy to see that D has a double bond there, and E has a triple bond. So actually, we're going to put D and E. Probably the most difficult one, and the one people may have missed out, is C, and they might have said, well, surely this contains C bonds, doesn't it? Well, yeah, it's got some C bonds here and here, but these bonds in between in the benzene ring are not, strictly speaking, carbon-carbon single bonds. Remember their bond length, I can't remember off the top of my head, but it's like 143 or something. It's in between the single 154 and the double 133 kind of bond length. So it's an in-between bond length. It's not strictly speaking a carbon-carbon single bond. Okay, which hydrocarbons are alicylic? And what this means is which hydrocarbons contain a circle, a cyclic group, and they do not have a benzene ring. So you should see which are a carbon ring, but not benzene ring. So we don't want a benzene ring. We don't want the delocalized pi system, whatever. We just want a normal ring. And so the two with a normal ring are going to be this bad boy and this bad boy, A and B. So we're going to go A and B for our answers there. This does not count because this is aromatic, not alicylic. These two are alicylic. This one contains like a 5-carbon ring, and this one a 1, 2, 3, 4, 6-carbon ring. Okay. Which hydrocarbons have the general formula CnH2n? So CnH2n, that's normally alkenes, isn't it? So it's definitely D, because D is like an alkene. And then let's just check the others. You could write it all out and find out what it is. If we really wanted to be long, we'd write it all out. So you go like that. Let's check E. 1, 2, 3, 4. Bish, bash, boosh, bish, bosh. Can't have any there. Yeah, bosh. So this has got 1, 2, 3, 4, 5, 6 H's. So this is C4H6. I may have got that wrong, folks, but it's definitely not double bubble. It's not C4H8, is it? Yeah, kind of one there, kind of one there. Yeah. So this is C4H6. So this does not have that general formula. We've already established that's an alkene. You probably remember off by heart the general formula for alkenes is CnH2n. And then we can go look here. This isn't going to be the same. This is, I know, but I'm just going to show you. It's long. I know it's painful, very, but I'm going to show you anyway. So this has got a hydrogen here. We got a hydrogen there. Oh, we haven't got a hydrogen there. What am I doing, you idiot? You can only have 3 bonds around a carbon in benzene because 1 electron is put into the ring. So that would have 3 there. There. This would have 2. And this would have 3. Now I've got to add it all up. What a pain in the butt. Why did I do this? What a pain in the butt. Right, we've got 1, 2, 3, 4, 5, 6 carbons, 7 carbons, 8 carbons, 9 carbons, 10 carbons. So we got C10. Right, do we have H20? I know this is a bit long to check this. You can just do this off the top of your head, but 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, we don't. I don't know if it's C14. I haven't probably calculated that, but it's definitely not. I probably haven't added that up right. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Even if I've made a bit of a boo-boo there, that's definitely not going to be C10H20. So, well, yeah, that is not one of them. Right, let's check B out because it's kind of got this double bond. Now, if it was just a cycloalkanes do have the formula CnH2n. We'll come on to that in a sec. But you can see here that's going to be bish, bash, bosh, bish, bish, bosh. 6, 7 carbons. So we got C7 over here. And then we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then, oh, is this? No, this ain't going to make it. 12. No, so that's going to be something like that. I may be wrong, but that's going to be something along those lines. C7H12. So again, and then over here, that is a cycloalkane. I know off by heart that cycloalkanes are CnH2n. So that's one that you can learn off by heart. It's very common. They've got the same formula as the same general formula. Cycloalkanes, which are saturated, have the same general formula as alkenes. And I could add it up for you if you really want to get excited about it. We go like that. 1, 2, 3, 4, 5. So we've got 6 carbons, C6. And then we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then we've got 1 coming off there, 12, because you've got to have 4 bonds around each carbon. So C6H12 for that bad boy. So there we go. Oh my gosh, am I taking a long time with this? Right, next one. What is the systematic name of hydrocarbon C? Oh, well, I've graffitied all over that. That's going to be impossible to work out what's going on. So what's the systematic name of hydrocarbon C? Let me rub this all out because there's no way I can do this with all of this orange stuff all over it. Okay. So straight off the cuff, we're looking at what is the main bit. The main bit's benzene. So the main name here is benzene. But then we've got some sides. We've got some sideman in the place. So we got an ethyl group. How do I know that's ethyl? CH3, CH2. So we've got an ethyl attached and we've got 2 methyls attached. So ethyl comes before methyl. So alphabetically, I'm going with ethyl first. And the ethyl group is more significant than the methyl group. So not only does it alphabetically come first, but in the numbering system, it comes first. So we're going to go 1 ethyl. What is that? That's going to be 2, 3, 4. 2, 4 methyl. Oh, hold on a minute. I've got 2 methyl, so 2, 4 dimethyl, and then benzene. In fact, I think I'm going to get rid of my. Oh my gosh, I can't spell what is going on. Benzene. Zing. Let's get rid of that benzene. We don't need that name anymore. We bust it out properly there. I probably could do with an extra hyphen or 2 in there. Could put a little line in between the 2 and the 4 if I want. Let's bust a little line there. It's coming out orange. Never mind. That happens. A bit Donald Trump. But there we go. 1 ethyl, 2, 4 dimethylbenzene. Bish bash bosh. That's going to get us another mark. Oh gosh, I didn't even write it in the right place, did I? Okay. Now, last one. I'm going to clear the screen for. We're going to zoom in a little here. Last part to this. Explain why hydrocarbon D is a stereoisomer. Let me zing in. Oh my good gosh, have I got the space? Yeah, we'll go with it. Okay, explain why hydrocarbon D, this one here, is a Z. Okay, that's important. Stereoisomer. Well, each carbon of the double bond has 2 different groups attached. So that tells us why it's a stereoisomer. But why is it a Z stereoisomer? Let's check it out and then we'll put the wording down. So this, let's call it, well, we got kind of carbon 1 and carbon 2. You can call it carbon X and carbon Y, whatever. Whatever makes it easy for you to chat about. But essentially, you've got a methyl group here. This is an ethyl group, right? So we've got a methyl and an ethyl on that side. And on this side, we have a methyl. And there, where you can't see anything, is obviously going to be a hydrogen. And here we go. Remember, stereoisomers come because there's no rotation around the double bond. So that's how you can get these stereoisomers form. We need to explain why it's Z and not E. So what you do is you go to the first atom attached to the bond and you look at if the groups are different, like these are 4 different groups. We've got, well, three different groups, but you get the idea. Right, we've got two different groups attached to each carbon. So straight away, that means it's definitely a stereoisomer. If I had a CH3 here and a CH3 here, it's not a stereoisomer. If I had a hydrogen here and a hydrogen here, it's not a stereoisomer. You need to have different groups, two different groups attached to each of the carbons on the double bond. Anyhow, now that I've waffled about that, we're going to establish which one of these is high priority, which one is low priority. And this is the SIP, the Channing Gold prelogue. Okay, so principles, let's do it. So carbon has an atomic number of 6. Hydrogen has an atomic number of 1. So what we're going to say is, well, the methyl group up the top here is high priority. Now we're going to look on the same side. We have an ethyl group, and that has an atomic number of 6, and the methyl group on the opposite atomic number of 6. But what you do there, where you get a draw, is you move to the next atom attached. So the next atom attached along that chain is a carbon with a 6. There's no extra atom attached here. There's just a hydrogen with a 1. So you can say 6 beats 1. Or what you can do is whatever. You could add the total of that ethyl group up and say that is 29 atomic number, sorry, and this is 15. So 29 beats 15. So you can do it in different ways. However you want to explain it, this is also high priority. And because this has a lower atomic number than the ethyl, it's low priority. And because the hydrogen is lower than the methyl, it is low priority. So we just need to say, let's put that into words. So it is a Z isomer as both high priority groups. The methyl and ethyl are on the same side of the double bond. And I think that would do the trick. Louise, she's Louise. And I'll just go that little bit extra and repeat it, but in the reverse, because you might argue it the other way. And you could say both low priority groups are on the bottom side or underneath of the double bond or below the double bond, or I'm just going to say are on the same side of the double bond. All of those other things would be the same. So this is, you could say that both of the low priority groups are on the same side of the double bond. And remember, there's no rotation around the double bond, so it's not like this low priority group can rotate there and the high one there, and they can become like a E isomer antigen opposite. They can't do that. And if I want, I can explain that on the, if you wanted to go into detail, you might want to explain it like this. On the first carbon, the methyl on top of double bond is high priority compared to H atom underneath. And then I'm going to run out of room, so I'm not going to bother with this explanation. I was going to go into a bit of a long one. But I was going to say, like, you could say that the methyl group here, you could put this into writing if you prefer this explanation and say the methyl group on top of the double bond is higher priority than the hydrogen on the other side opposite it, underneath the double bond. And then you could say the ethyl group also on top of the double bond is high priority compared to the methyl group opposite it on the underneath of the double bond. Therefore, both high priority groups, the methyl and ethyl, are on the same side. Hence, it is a Z isomer. But there we go. That was just me going with an extra explanation. All right, guys, don't forget sharing, caring, hit the like, punch up the bell, subscribe. I'll catch you lot on the next video. And don't forget, remember. Listen, Marty Tucker's hit the like. Do you understand? Because like it's painful when people don't hit the like. All right.
This question is about the reaction of alcohols. There are 4 structural isomers C4H10O that are alcohols. CH3, CH2, CH2, CH2OH, that is butan-1-ol, I believe. CH3, CH2, CHOH, CH3, that's going to be butan-2-ol. Then we have CH3, 2, CH2OH, that's going to be like methane, 2-methapropanol. And then we've got CH3, COH, which is going to be like 2-methapropan-2-ol. Okay, these alcohols take part in different types of chemical reaction, including elimination, oxidation, substitution, esterification. For each type of reaction, choose the appropriate reagent, that means the appropriate reactant, and or catalyst if you need them, and show the organic product formed. The first one to do is the elimination reaction of butan-1-ol. What's the reagent? What's the catalyst? Why don't you press pause on the video, grab pen, grab paper, have a go at this one, and then unpause and watch the explanation. Okay, as you know, I'm going to go through this in detail. Don't forget to share, like, all of that business. Really helps me out if you can share this with any other students taking A level that you know in your class. It will help them as well, and it will help me. Okay, so I've drawn the display formula of butan 1-ol out here. Now, what we actually require, the reagent is, or catalyst, it's kind of both, is sulfuric acid. You could do phosphoric acid. You can even use aluminium oxide. Now, what happens is your hydrogen ions, a pair of electrons from the oxygen on the alcohol group goes to the hydrogen ion. This forms that oxonium ion where you have the positive charge on the oxygen. In order to get rid of that positive charge, that bond to the carbon breaks and we end up with water separated, and then we have a carbocation. Now, to neutralize the carbocation, a hydrogen adjacent to the carbon that had the hydroxyl group, so always the hydrogen adjacent on a carbon adjacent to the carbon with the hydroxyl group, will donate its electrons to form a double bond, and that's what we get with dehydration. So we're going to end up with but1-ene. We've lost the water. In fact, the sulfuric acid's a catalyst, so it gets reformed. And you can write that as displayed formula. You can write that as structural formula, CH3, CH2, CH2, or you could do the skeletal formula, which I'm always pants at, but there's my attempt today. And that's worth 2 marks. Okay, let's zing to B. Oxidation of CH3, CH2, CHOH, CH3. That is going to be butan 2-ol. What's the reagent and or catalyst? Well, it's oxidation, and the alcohol this time is on a secondary alcohol, not a primary like in our first one. And so that's going to tell us what specific substance it's going to form during oxidation. So I'm just drawing out butan 2-ol here, and hopefully you know what's the oxidizing agent for alcohols. You know, if it was a primary alcohol, we were oxidizing it, go to carboxylic acid. Eventually, if you refluxed it, it would go aldehyde, then carboxylic acid. How do we know this is a secondary alcohol? Look, it's got 2R groups. I've drawn them there. So 2R groups attached to the carbon with the hydroxyl group, so it's secondary. And secondaries go to a ketone. And the oxidizing agent is going to be potassium dichromate, acidified, you could write, or you can add hydrogen ions to show that it's acidified, or you can name an acid like sulfuric acid to acidify the potassium dichromate. You can just write H plus ions and Cl2O7 minus ions, which is chromate ion, dichromate ions, acidified dichromate ions, and it's going to make, that's the functional group we're going to make. We're going to get the ketone. Of course, that's going to get rid of that OH group and the hydrogen above the carbon, and you're going to end up with water coming off as well, but they want the organic product. They're not interested in the inorganic water molecule that comes off. So butan 2-one is our organic product. So we're going to draw that out as the display formula, or you can bust out the skeletal or structural. Don't forget to pause the video each time to have a go at these before you go through and check out your answer. Okie dokie. So we've got a reagent, K2Cl2O7, a catalyst, hydrogen ions or acidification, or saying it's acidified, H2SO4. And we've got an organic product to get the 2 marks. And the organic product, you can see I've got the skeletal, the structural, or the displayed. Any one of those is going to get you the marks. So there we go. Don't forget, when we write the equation, the dichromate ions, we just represent as an O in the brackets. You can't do that here. You have to actually name the reagent, the K2Cr2O7. Okay, you can swap the K to Na because that's a group 1 element. It's not going to make much difference overall. C, substitution reaction of CH3 to CH2OH. What is that? That's 2-methopropan-1-ol or 2-methopropanol. And you need to name the reagent and the catalyst. Why don't you, I'm going to go through and explain it by drawing it out and showing you the reaction that takes place. But why don't you go through and pause the video, have a go, and then unpause and watch the explanation. Okay, so what I've done here, I've drawn out our compound, which is 2-methyl-propanol. Remember, you name the methyl group because you number the methyl group here. It's the side E. Basically, it takes second place to the alcohol group. The alcohol group has more importance. Now, the carbon that's joined to the oxygen is going to be delta positive, and that leaves it susceptible to attack by nucleophiles, things like chloride ions. So the chloride ion is going to attack that carbon there because it's negatively charged, going to donate a pair of electrons to that positive carbon and form a bond. And of course, the carbon can't have 5 bonds, so the OH is going to break off. We've got nucleophilic substitution. Now, we just need some sort of reagent that contains chloride ions and that dissolves, in solution. So we're looking at an ionic compounds, something like sodium chloride or potassium chloride. Both of those will dissociate completely as salts to release those chloride ions. Um, we want to acidify them so that there are hydrogen ions knocking about to pick up that, mop up that OH group that comes off. So we're going to use sulfuric acid. And now we just need to write the organic product. And all you've got to do is copy out what they gave you in the structural formula there, and then just swap for Cl the OH. Easy peasy, right? If you want to make it a little bit more complicated, you could try to do the skeletal formula, which is always a bit of a bummer. You've got to count up how many carbons there are attached. Is that right? I think so. 1, 2, 3, 4. Yeah, that looks right. Okay, that's 2 methyl. Oh my gosh, what is that? 2 methyl. 2 methylchloropropanol. Oh gosh knows. 1 chlora, 2 methapropan. Something like that. Propane. Yeah, whatever. You don't have to name it here, and I'm not making a very good job. I got the flu at the moment. It is winter, and I am feeling like poo. Right. Don't forget to hit the like, guys. People watch the videos. They seem to do all right, but people never hit the like. The esterification reaction of CH33COH, reagents and or catalyst. Why don't you pause the video and have a go? See if you can work out the esterification of an alcohol. You should be able to do this one. Okay, so what I'm doing is I'm drawing out the molecule. God knows what this is. 2-methopropan-2-ol. Not been very good at my naming today with the old cold. Right, let's go. So here we go. It doesn't really matter. We want to form an ester link. What do alcohols react with? They're going to react with a carboxylic acid. So hopefully you got that. Now you could name any carboxylic acid. You could go methanoic for the simplest one. I'm going to do ethanoic. It's also another simple one that comes up a lot in esterification reactions. So we've got ethanoic acid here, CH3COOH, and we are going to acidify it. Now, if you're going to use ethanoic acid, you need to acidify it because it's not as reactive. You could do acyl chlorides like ethanoyl chloride. Love that. Ethanoyl. Acyl chlorides have that OYL in them. Now they're going to react and you're not going to need to acidify them. Okay. However, they're a little bit dangerous because they form HCl, so probably less likely to do in a school or college laboratory. So we're going to go with the ethanoic acid. And how are we going to draw out what gets made? Well, all you're going to do is replace. So I'm drawing out the displayed formula of what we're starting with. With esterification, you're just adding something on, aren't you? You suppose you're removing the water as well, condensation reaction. But you've got the OH bond going on here. Now, what we're going to do, I'm going to draw the carboxylic acid out. So here is the carboxylic acid functional group, ethanoic acid, and all I need to do is remove a water molecule. Now I can remove that or I can remove that. It doesn't really matter. The end product's going to look the same, okay? So I'm just going to zing this over and join these together, and there's my final product, which will give me the marks for the organic product. Don't forget, if you're going to say that you're using a carboxylic acid, you must use an acid catalyst to acidify it. Okay, so you've either got to do hydrogen ions, you say with hydrogen ions, or with sulfuric acid, a suitable acid catalyst. Okay, this is the structural formula. Hold on, that says cocoa. CH33, cocoa CH3. What the arse? Okay, let me put them the right way around. COOCCH3. Can be a little bit difficult sometimes. I always prefer the displayed formula when given the option. So I've circled you can see the bits, how you add it together. So there we go. Right. You could do skeletal for this as well. I'm not even going to attempt to do that at the moment. But yeah, make sure you leave any comments, anything like that. Hit the like, all of that business. So why don't you read through the question, press pause on the video, grab pen, grab paper, have a go at the question, and then unpause and watch my explanation. Let's go. Okay, haloalkanes can be synthesized by reacting alkanes with halogens in the presence of UV radiation. An alkane reacts with bromine to form 2-bromo-2-methylpropane. Write the equation for this reaction, so that's going to be worth 1 mark, showing the structures of the organic compounds. And then the second mark is for naming the reaction mechanism, and the third mark, the type of bond fission that occurs. So I'm going to go through the explanation now. So again, if you wanted to go through it first yourself or have a go in your head or on scrap paper, better to do so now and press pause. All right. So what I'm drawing out here is the 2-bromo 2-methylpropane over here. You can see the display formula. Um, Now, I want to write the structural formula. This is what gets produced. So this is on the product side of my equation. So I'm going to put CH3 in brackets with a 2, and then CBr, and then CH3, and that's going to be my structural formula. Again, whether I put the Br in brackets or not, I think isn't really going to affect whether we get the marks. Now, we know that we're doing an alkane plus bromine, so I know I'm going to do something plus Br2. Now, I just got to work out what alkane will that be. Well, look, instead of the bromine being there, I just want to replace that with a hydrogen. So let's write this out exactly the same. CH3, 2, CH instead of CBr, and then CH3. And there we go. That is our two reactants done. What's that? 2-methylpropane, and then it's becoming 2-bromo-2-methylpropane. So we got substitution, we got the swapping there, kind of free radical substitution. So the hydrogen and the bromine are going to end up getting swapped. Okay, so what type of bond fission? Well, if you think about it, we're going to need ultraviolet light to form those free radicals in the initiation reaction, right? We're going to use UV light. So what's going to happen? We're going to take the Br2, add UV light, and we're going to get 2 bromine free radicals. Now, some people have issues with how do you know whether this is homolytic or heterolytic? This is actually homolytic fission, and that means that one unpaired electron goes to each of the atoms from the bromine molecule. So look, here's my bromine molecule. I'm doing crosses and dots. Imagine that's covalently bonded. Imagine UV light splits that, and they go back to basically being bromine atoms. And that means in a bromine atom, 7 electrons in the outer shell, there's going to be 1 that's unpaired. Look, I've circled them in green there and there. So that's what we mean. That's homolytic fission. Now, the opposite of that would be heterolytic fission, which is where you'd have both go to 1 and it would be negative and the other would be positive. All right, let's move on. So describe 2 limitations of the synthesis of 2-bromo-2-methylpropane from an alkane and a bromine. So when you do these free radical substitutions, the problem is you can't control the exact products you're going to get because there can be further substitutions and there can be different termination steps as well. So you can get, when you have those propagation reactions which make the free radicals, we can get further substitutions along the chain. So we might get like we might get 1,2-dibroma 2-methylpropane, for example, or we could change the position of the substitution of the bromine. The bromine we might end with 1-broma 2-methylpropane. So just a mono substitution, but at a different position. The bromine could substitute at a different position. I'll show it here with this green crusty little skeletal formula. Actually, I need to rub that. Hold on, bear with me one sec. And there we go. So here you can see that I've got like 1-bromo 2-methylpropane, but I could also have dibromo, tribromo. So it could be multiple substitutions, and different termination steps could result in different products. And that's it. And so for this next part to the question, what you've got to do is fill out the flow chart below, complete the flow chart by filling in each box. Why don't you pause the video and have a go at these first 2 boxes worth 4 marks. So you've got how do you go from bromoethane to an amine and what's the reagent? And how do you go from bromoethane to an alcohol and what's the reagent? Pause the video, have a go now on some scrap paper, and then unpause and watch the explanation. Alrighty then, so the carbon's going to be delta positive, the bromine's going to be delta negative on the bromoethane. Imagine an ammonia molecule comes and attacks it. Well, that ammonia molecule is going to want to join, is going to want to attack that delta positive carbon and form a bond there. And of course, we know that carbon can only have 4 bonds. So one of our reagents is going to be ammonia. And we're going to do this ethanolic, so ethanolic ammonia, and that's going to get you 1 mark. And then we need the amine that's formed. But I'm just going to talk you through the mechanism as well, Matt, as well. So essentially what's going to happen here is the ammonia there is going to join on, the bromine is going to snap off, and what you're going to be left with is NH3 attached to that carbon. That means you've got 4 bonds, a nitronium ion, which is positive. A second ammonia molecule will come and remove one of those hydrogens, its lone pair attacking that hydrogen. So you'll be left with an amine, and we're going to be left with ethylamine here, CH3, CH2, NH2. And I should really write that out in displayed. I should display that, but yeah, I'm not going to bother. So yeah, you could display that if you want. You get the coup. That'll get you 2 marks. Now, if we come down to the right-hand side, we can check how is bromoethane going to make an alcohol. Well, you're going to react it with sodium hydroxide, aqueous, to make sure there's loads of OH minus ions around. That's going to ensure that it forms ethanol. Nice and simple, right? We're going from bromoethane to ethanol. And the hydroxide ions are going to attack the carbon, which is delta positive. The bond with the bromide ion is going to break off. And so we're going to get ethanol formed. Lovely jubbly. And this is done aqueous. The hydroxide ions are actually, it's favored the carbon hydroxide bond rather than the carbon halogen bond. So you're going to get CH3, CH2, OH. And that's going to be 2 marks. You could use KOH if you want, potassium hydroxide solution. Anywho, let's move down. Now we're going to look at bromoethane and how does it become a nitrile, and what is the reagent needed, and we go through the mechanism for that as well. So you want some nitrile or nitride, whatever you call them, cyanide ions or nitrile ions, and you're going to get them from using KCN or NaCN. And you're going to want to do that in ethanolic rather than aqueous or acidified. You want to use ethanolic. So KCN ethanolic, that's going to give us these nitrile ions that are going to attack that carbon. And again, you're going to get nucleophilic substitution here. So the bromide ion is going to be kicked out. And why ethanolic? This prevents side reactions. If you did it in aqueous, you'd have loads of hydroxide ions about, and the OH minus ions, you'd start to get competition with the nitrile and the OH minus ions to join onto the carbon. So you get a mixture of alcohol and nitriles, which is not what we want. So yes. So yeah, potassium cyanide, lovely jubbly. You could use hydrogen cyanide, I guess, but that's, you need a fume cupboard and all of that. No, KCN ethanolic, stick with that. Right, let's zing down, zing down, zing down, zing down. What we want to do is move that up there, just clean this up a little for you. And then the next one is for us to decide there are 2 ways to attack a nitrile. And what we can do here, we can attack the nitrile and we can either form an amine or a carboxylic acid. So why don't you pause the video, have a go at that, and see if you can work out what the 2 products are and the reagents. Okay, so what we want to do, we want to dehydrate this, and instead of having a C triple bond to the end, we want a single bond to the end so we can turn it into an amine. We're going to need 4 hydrogens added there to make a CH2, NH2 instead of the CN with a triple bond. And we're going to use lithium aluminium hydride, LiAlH4. We want to acidify it, so we've got loads of hydrogen ions about. This is the kind of thing with a reducing agent where you put brackets with an H plus inside. You can use that as the symbol for a reducing agent, or you can just put H. That looks like an acid. Yeah, never mind. Right, whatever I'm waffling about. You can see 2 hydrogens have been added to the nitrogen and 2 hydrogens to the carbon that's attached to the nitrogen. We got rid of that triple bond and added 4 hydrogens, and that will give us the amine. Okay, now let's look at turning this into a carboxylic acid. So what we're going to need here, our reagent is going to be, what you kind of do here is you're going to turn it into blah, 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 blah. You're going to add hydrochloric acid as a source of, and we need hydroxide ions. We need hydroxide ions. So we're going to reflux HCl, which gives us hydrogen ions, and we're going to use it in aqueous for a source of hydroxide ions. Oh my good gosh, I'm getting tired now. So you're going to end up with propanoic acid. And there we go. Let's move on and get the next question done. Okay, question 19. This one's about alkenes and carbonyl compounds. Okay, so alkenes and carbonyl compounds take part in addition reactions. Describe one addition reaction of an alkene and one addition reaction of a carbonyl compound. Include reagents and the reaction mechanisms, it's worth 6 marks. Basically, 3 for each, 3 for the alkene, 3 for the carbonyl compound. Your choice, you choose. Pause the video, have a go on paper. Now I'm going to go through the answers. Awesome. Okay, so I'm going to stick nice and easy with my alkene. You could choose any alkene you want. I'm just going to go with ethene, right? Simplest alkene you can get. I'm going to attack it with bromine. Again, a nice simple reaction mechanism. You know what happens. The bromine molecule approaches the electron dense double bond. You can write that if you want. You can include that in your answer for some extra marks. And it polarizes the bromine bond, and therefore a pair of electrons from the double bond leave, shown by my curly arrow, to the delta positive bromine atom in the bromine molecule. Now that means that we get a carbocation form where one bromine has been attached, and the second bromine, which received a pair of electrons from the bond, is now a bromide ion. So the bromide ion will now attack the carbocation. And what are we going to end up with? We're going to end up with dibromoethane, but we want to say 1,2-dibromoethane. But you could just call it dibromoethane, because what else could it be if you've chosen ethane? If you've chosen propane, then you've got to number it properly when you form dibromo propane. But there we go. So additional information for this, you've got bromine and ethene are your reagents. We don't need any ultraviolet light because these electrophilic addition reactions happen readily. And obviously the test for alkenes, it decolorizes bromine water and we form dibromoethane. If you want, you can say the electron-rich double bond polarizes the bromine molecule. As a little bit of extra info, right, let's get on to the carbonyl compound and addition across that carbonyl bond. So I've gone easy. I could have gone with methanal, but I've gone with ethanal. So C2, C2H4O. And we're going to use acidified KCN. Now, noticed earlier, or sometimes we use ethanolic KCN. So ethanolic KCN is when you want to add a nitrile, you want to swap, do substitution with a haloalkane. That's when you use ethanolic, because you're trying to avoid forming an alcohol. With acidified KCN, what you're going to get, the nitrile, obviously having a lone pair, is going to attack the delta positive carbon, form a bond. Carbon can only have 4 bonds, so the carbonyl bond is going to break, forming that negative oxygen, as shown here with a lone pair and a minus symbol. Then we've basically got our nitrile added, so we've extended the chain. It's gone from eth to prop. And then our hydrogen ions, remember we used acidified KCN. You could have used NaCN, acidified NaCN as well. And that hydrogen ion is now going to join on, and we are going to get ethanol formed. And additional things here saying it's safer to use KCN rather than HCN. HCN, you'd need a fume cupboard. KCN, it will form HCN within the reaction mixture. It's a little bit safer. What's the name of this mechanism? Well, it's a nucleophilic addition reaction, because we started with a nucleophile. And also we form a hydroxynitrile. And if we want, we can name that 2-hydroxypropanitrile. Just noticed a mistake there in my name, 2-hydroxypropanitrile. You never want 2 N's together like that. That looks ugly. Put the E after the propan here, so it's propane nitrile. That way you don't get the 2 little N's together. Okay, let's move on and smash out another question. That'll get you all of the 6 marks. Okay, for this one, this question is about carboxylic acids and esters. Why don't you pause the video and have a go at this first one? Explain with a labeled diagram how HCOOH, that's methanoic acid, and how it interacts with water when it dissolves. So they want you to draw a labeled diagram, and that'll get you 2 marks. Why don't you pause the video, have a go? Right, I'm going to go through the answers. So let's go. First of all, we want to draw out our methanoic acid. And we want to draw our water, and you want to make sure that you have all the correct symbols. So here's methanoic acid, just 1 hydrogen, COO and an H. Make sure you put the delta positive hydrogen, the delta negative oxygen. And then we've got our water. We've got a lone pair on that water, and that forms a hydrogen bond, which is one of the intermolecular forces, with the delta positive hydrogen on the methanoic acid. And I'm going to do a second water molecule and show a hydrogen bond forming between the oxygen on the hydroxy of the carboxylic acid
and the delta positive hydrogen on the second water molecule. So I'm just showing you two hydrogen bonds. I'm going to label these as hydrogen bonds and then just label these as methanoic acid, although I've said metanoic acid. Love it. Dipolar water molecule. All right. Okay, ester F has the structure below. What is the systematic name for this ester? Why don't you pause the video, have a go at naming this one. All right, I'm going to go through the answers. So first of all, we can see it has an ethyl group coming off of the ester link. This normally comes from the alcohol. So remember, the first part of an ester's name comes from the alcohol, which forms the side chain after the ester link. And this is going to be the ethyl group here. Obviously, if that was 3 carbons long, it'd be propyl, 4 carbons long, it'd be butyl. Now we're going to look at the second part of an ester's name that comes from the carboxylic acid, or a carboxylic acid derivative. Could come from a carboxylic acid or from an acyl chloride. Let's have a little look. We've got carbon 1 here where you find the ester link or the carboxylic acid group. And then we go along there and we can see there's a side group coming off of carbon 4. It's 5 carbons long, so we're looking at pentanoate. But there's also a methyl group coming off of carbon 4. So we're looking at 4-methyl pentanoate. It would have been 4-methyl pentanoic acid or 4-methyl pentanoyl chloride if it was an acyl chloride that formed this ester. And we're looking at the ethyl being named first because that's the part that comes from the alcohol and the part you name first with an ester. So we're looking at ethyl 4-methyl pentanoate. And there we go. That is the name, even though I can't seem to get it written down properly. Forget the space. It's not really supposed to be a space there. You could slap an extra hyphen in there, then ignore that. But there we go. I can't sort that out. So let's move on to the next question. Right. Ester F can be prepared from a carboxylic acid in 2 steps. Step 1, the carboxylic acid is converted into an acyl chloride. The acyl chloride is then converted into ester F. Write equations for step 1 and 2 show the organic compounds as structures. So what they want you to do is write the equation that shows how that 4-methylpentanoic acid, the carboxylic acid, 4-methylpentanoic acid, how that got converted into an acyl chloride. So that's going to be like 4-methylpentanoyl chloride. So how would you change a carboxylic acid into an acyl chloride? Write an equation for that, and then write an equation to show how the acyl chloride is then converted into ester F. And there you go. Have a go. I'll say, so we're going to start with 4-methylpentanoic acid, so CH3 to CH2 to COOH. You could just write the displayed formula, or you can do this. You can write the skeletal formula, which is probably better. So easier to write skeletal, right? Oh my gosh, what am I doing? 1, 2, 3, 4, 5 pentanoic acid. I'm going to check out the diagram. So you can always scroll back, have a look at the diagram, or just flip up the page when you're in an exam and just copy down because they had the exact structure there. So there we go. Just double check my skeletal structure. That's pentanoic acid. Now I'm going to react it with not SO2, sulfur dioxide, thionyl chloride, so SOCl2. When you want to make a carboxylic acid, this is the way to do it. When you want to change a carboxylic acid to an acyl chloride, this is the way to do it. And essentially your chloride ion is going to attack there, the hydroxide is going to break off, and we're going to end up with our acyl chloride, our 4-methylpentanoyl chloride over here. So you just copy the skeletal formula. The only thing you're swapping is the OH for a Cl. Now you need to get rid of the O. Well, the O joins with the SO to make SO2, and the H from the hydroxide group joins with the leftover Cl to make HCl. So 1 Cl goes there, and you can see that all balances up. Beautiful, wunderbar. And so I'm going to redraw the skeletal formula now for my 4-methylpentanoyl chloride. So I've got my acyl chloride, and that is now going to just react with an alcohol to form the ester. The beauty of this is we don't need the H2SO4, the sulfuric acid, because you do need acid catalyst if you're doing a carboxylic acid and alcohol to make an ester. That type of esterification needs a sulfuric acid, but we don't need that in this situation. That's why acyl chlorides react more readily to form esters. And there we go. There's the correct structure of the ester, which I've just copied from above. It's identical to the one above. And that's going to get you 4 marks. Lovely. All right, let's move on.
So for this next one, you want to look at this repeat unit of a polyester, draw the structures of the monomers required to make this polyester. Basically, split that into two molecules. Both molecules have identical functional groups. And yeah, it should be nice and easy for you to do. Pause the video and have a go. Okay, so just identify the ester link between these two. And you want to add water back onto both. So H2O there, add an OH there, whack an H back on the other end. You get the idea. You're going to add two water molecules to break this, return this into its two monomers. One to split the link that's linking the two molecules, and then a water molecule to either end, basically. So what you're going to end up with is your kind of dicarboxylic, dibenzoic acid, whatever the hell this is over here. Lovely jubbly. Add the water back on. And then the other one's going to be a diol. So you're just going to add your OH there and your OH there. And there we go. All the marks. Easy peasy, lemon squeezy. Okay, now this last question is a bomber. So this one is super hard. D, the compound below contains an ester and an amide group. So don't punch yourself in the face. You make mistakes here. There's my alarm going off. Draw the structures of the organic products formed from the complete alkaline hydrolysis of this compound using sodium hydroxide. Worth 4 marks. The clue I'll give you before you pause the video and have a go with your paper and pen and your whatever. What I would do is you want to break when you when you do alkaline hydrolysis of this molecule here, a little bit more complex structures. So you've got amide links and ester links. You want to break all the ester and amide links and see what different molecules you can make. You basically want to try and come up with 4 different structures based on breaking the ester and amide links. Okay, it's worth 4 marks, 1 mark for each structure. Pause the video, have a go. So the first thing I'm breaking here, you can see I'm mashing up this ester link here, which is going to release the alcohol from that kind of ester that's attached to that carbon chain ring. And I'm going to get a methanol group coming off of there. Then I could break the bit in between and we could kind of get a methanoate. And what am I trying to do here? No, that was going to be a methanoate ion, because if I take that carbon off there with that carboxylate, that's going to be I'm going to get methanoic acid. But remember, it's alkaline. So we've got to circle that in pink. I've done that with a little question mark. It's alkaline. That means the hydrogen ions, excess hydrogen ions on any carboxylic acid groups are going to be removed. Okay, so we're going to have our methanoate ion here. So I've got kind of got methanol and then some sort of methanoate ion. Now I want to concentrate on breaking those amide links. If I break the amide link here, I'm going to go between the carbonyl group and the amine. Remember, an amide has an amine group attached directly to a carbonyl group, but we're going to break that amide link, so we're going to have to sever this ring. All right, no diddy. And you can see there I'm returning the amine group to normal. Got my carboxylic acid there. That looks good. That's another separate molecule that's going to be made. You could potentially put a hydrogen there and a hydrogen here if you wanted, just to show that a hydrogen atom would form there on the ring, because remember, our carbon needs 4 bonds. I guess I could put 2 hydrogens there if I wanted. It doesn't really matter what I add. Oh no, it's no. I don't. Yeah, I'd need to put 2 hydrogens. It doesn't really matter what I attach there. Really, I could just leave it as skeletal. I don't need to put those 2 pink H's there. Right. Let's get on to the 4th structure. Now, in the 4th structure, I need to put my other hydrogen on the amine here. What I can do is I can sever there to leave the methanoate ion still connected to the ring and break the amide link there. And so I end up with like a 4th structure. And then I can attach an OH, but then that's a carboxylic acid. That H is going to be removed. So I should really remove that OH. I should remove that H and leave that as well as an oxygen with a lone pair and a negative charge as well. And that will get you all the marks. Lovely jubbly. Okay, let's get into this one. This one's a question about aromatic compounds. That's compounds containing a benzene ring. Why don't you read through the question, pause the video, have a go at each stage, and then unpause and watch the explanation for each stage of this question. All right, let's get into it. So question 21, this question is about aromatic compounds. Ethyl benzene C6H5 CH2 CH3 can be prepared by reacting benzene with chloroethane CH3 CH 2Cl in the presence of AlCl3. The AlCl3 acts as a halogen carrier. Here we've got the ethyl benzene structure. In the mechanism, chloroethene reacts with the halogen carrier to form a carbocation, which acts as an electrophile. What is meant by the term electrophile? And that's worth a mark. And then outline the mechanism for this reaction, including the role of the AlCl3 as a halogen carrier. Why don't you grab a pen, grab a bit of scrap paper, press pause on the video, have a go, and then we'll go through the answers and see how much of these, see how many marks you can get. Awesome. So first up for 1 mark, what is meant by an electrophile? An electrophile is essentially anything that will accept a pair of electrons, things that are attracted to electron dense or rich areas. Now we're going to get into the mechanism. So first off, let's look at, well, it says in the presence of a halogen carrier. Let's look at how the halogen carrier enables a strong electrophile to be formed. And what the halogen carrier does is it reacts with the chloroethane that I've circled in pink, CH3CH2Cl, and it strips it of its chlorine atom, and that becomes AlCl4 minus, so an ion, and leaves us with kind of like a positive ethyl electrophile there with that positive charge. Okay, and that is going to be a strong electrophile that can attack that benzene ring. Okay, now what we want to do is show how that positive electrophile, that strong electrophile formed with the use of our halogen carrier, attacks that benzene ring. Now it's kind of optional here. I'm writing CH3, CH2, and then it's a, oh gosh, CH3, CH3, no such thing exists. Well, it does, cetane. But there we go. Right, let's put a positive charge there. Now, look, my positive charge, is it on the hydrogen? Is it on the carbon? It's kind of like, where do you draw it? Okay, I might want to flip my electrophile around and write H3CCH2 like that, put the plus charge on the carbon atom, then we could draw the arrow going there. Very important as well that your arrow from the benzene ring is touching the ring of the benzene ring and not coming from the center of it. They won't give you the mark if your arrow is just loosely coming from the center of the benzene ring. Make sure it's coming from the actual ring, those pi electrons. Okay, now we're going to draw the broken ring in the next stage. Make sure the tips of your broken ring do not go past the carbon atoms or either side of them. So carbon atoms, like, what is that? Carbon atoms 1 and 5. Make sure it doesn't go past those. And then I want to draw the hydrogen and the ethyl group both attached to the same carbon. And therefore, in order to reform the delocalized ring, the hydrogen donates its pair of electrons to reform the ring. What do you call a hydrogen atom without a pair of electrons? We call it a hydrogen ion. It has no electrons. So we're going to get a hydrogen ion formed here. We've got our ethyl benzene, hydrogen ion. Now, what happens to that hydrogen ion? If I want to get all 5 marks, I need to show the reformation of the halogen carrier, the AlCl3, which just temporarily carried the halogen. And that happens because the hydrogen ion that is released reacts with the AlCl4 minus ion and forms hydrogen chloride and reforms the AlCl3. And that's going to get you 1 mark for the electrophile term and 5 marks for the formation of the halogen carrier and the reformation of the halogen carrier. And yeah, you get the idea. The formation of the electrophile, reformation of the halogen carrier, and then 3 marks down here for the mechanism. I guess it's 1 mark for the arrow to the electrophile in step 1, and then 2 marks probably, 1 for the broken delocalized ring with the positive sign, not too far, make sure it's a U shape, and then 1 mark for the hydrogen donating its electrons back to reform the ring for the final step. Bosh! Okay, part B. The table shows the directing effects for different groups in the electrophilic substitution of aromatic compounds. So we have 2,4 directing. You've got the phenol, the amine, and the kind of amide group there. And all of those are directing groups. They donate electrons to the ring, and especially to the regions at 2, 4, and they're making it much more likely for species to electrophiles to attack those regions. And then we've got 3 directing. They direct things to the 3rd position. They do that by stripping, by withdrawing electrons in the 2, 4 positions, so that the 3rd position is more electron rich and more favored. Right, this is mono substitution, so we just want to add a chlorine atom here. It's the 3 directing, so we want to add it to the 3rd position. Why is it 3 directing? That nitrile group or cyanide, whatever, the CN has withdrawn electrons from the 2 and 4 position, leaving the 3 position more electron dense, and so more likely to be attacked by an electrophile. Now we have the 2,4 directing. These donate electrons to the 2,4 position, making them more electron dense. But remember, it's mono-substitution, so an easy mistake to make here would be to misread the question and to add a chlorine here at position 2 and then again at position 4. That would be double substitution. We want mono substitution. So if you didn't get that right, RTFQ, Marty Tuckers. Right. Yeah. And then it wants us to show all the organic products. So we have to show both types of mono substitution. So we're going to show the chlorine now attached to the 4th carbon, which is gonna be there. Okay, and although it says 2,4 directing, it, you can get 2,4 and 6 with these things normally. Okay, there we go, 3 marks. Lovely. Wunderbar. 2. The reactions C6H5NH2 are similar to the reactions of phenol. So the reactions of aminobenzene, or whatever that is, are similar to the reactions of phenol. Write an equation for the tri-substitution of C6H5NH2 with chlorine. So that's just testing you on the 2, 4, and 6 position. Okay, so we want to write out C6H5NH2. Now we want to attack it with chlorine. The chlorine is going to substitute. Remember, on a benzene ring, there is a hydrogen atom at all of the points, except for the one with the NH2 attached. Why the hell have I put C6H5NH2? Why have I attached another benzene ring with an amine? Sorry, let me just correct that. So what we want to do here is just show that it's tri-substitution. I want to add a chlorine to the 2, 4, and 6 position. And obviously, there's a hydrogen at each of these positions as well, which has to donate its electrons back to the ring to stabilize the ring as each one is added. So we're going to get 3 hydrogen ions released. They're going to join with 3 of the chlorines. So we're going to need 3 molecules of chlorine, 6 chlorines in total, 6 chlorine atoms in total, 3 with a hydrogen, and 3 to be substituted onto the ring. And that's going to get you both the marks. Now, for the next part of the question, it says, explain why chlorine reacts much more readily with C6H5NH2 than with benzene. So what is it about the C6H5NH2? Well, it's the NH2 is kind of has an electron inductive effect, or it donates electrons. The lone pair from the NH2 or the nitrogen, is partially delocalized into the pi ring, making it more electron rich in those areas 2, 4, and 6, making it much more likely to be attacked by an electrophile, much more attractive to electrophiles. Welcome to Let's Get to the Marks, going through an A-level chemistry question on amino acids. Why don't you grab some paper, grab a pen, calculator will be needed, pause the video, have a go at this one, and then unpause and watch me go through with the explanation. All right, alpha amino acids have the general formula RCHNH2COOH. The R group in an alpha amino acid contains carbon and hydrogen only. This R group has a molar mass of 91 gram per mole. A polymer is formed from 500 molecules of this alpha amino acid. Determine the molar mass of this polymer. Give your answer to the nearest whole number. Let's go. Press pause on the video, grab your pen, grab your paper, grab your calculator, have a go at this one. All right, time to go through it. So what I'm going to do first of all, we've been told that the R group is equal to 91. Let's work out how much a standard amino acid, the constant region of an amino acid, what it's worth. So I've got the carboxylic acid group, I can't speak. I've got the amino group, or amine group, and then I've got the R group. We know the R group is 91. Let's work out how much the others are. So amine, nitrogen's 14, H's are 1, the O's are going to be 16 each, that's 32 for the 2 O's, 1 for the hydrogen there, 33 plus 12, that's 45 for the carboxylic acid group. Then I have 1 and 12 for the one with the R group, so that's 13 for that. And then what's that? Amine is 14 plus 2 is 16. Great. Now just going to whack it all together. 58, 13, and 45, 68, 74. Okay, so it's 74. Now, if that R group was just an H, was the simplest amino acid, we'd have 75, but it's not, it's 91. So we want to go 91 plus 74, and that's going to give us the total molar mass of this amino acid, and that's 165. Now, when you join 500 of these molecules together, it sounds obvious, really, but you times this by 500. But it's not quite that simple, is it? Because when we join these molecules together, we're going to lose some mass in the form of water because we call it condensation reactions. And now we need to just work out how much we're going to lose. So you get at least 1 mark for this. Working out the total MR of 500 molecules would be 82,500, but that's not taking into account the mass we've lost. Each time we join one of these together, we lose a water molecule. So we're going to lose 18 MR each time we join one together, and there are 500 of them stuck together. So we might want to say, hey, minus 500 times 18. That makes sense, right? However, that wouldn't be taking into account the fact that on the right hand and left hand side on the end of the polymer, a water molecule would not be removed. So it's actually 82,500 MR minus 499 times 18. So minus 499 water molecules. The 18 comes from the two H's and the O, which is 16. So yeah, remember, you don't remove the final water molecule. The ends of the polymer are kept intact. You have both hydrogens on the amine and the OH group on the carboxylic acid. So your final answer should be 73,518. Pat yourself on the back if you got it right. Right, part B. The amino acid below can form addition and condensation. Polymers draw two repeat units of these polymers, display the sections linking the monomers together. Pause the video and have a go. Okay, main thing to remember with addition polymerization, just get rid of the double bond so it turns into a single bond. Keep two C's in one unit and then everything else tuck off underneath or up the sides, right? So basically I need to do two of them CH, two of that kind of amino acidy group at the bottom there like that. I don't know how it's best to write that. Maybe it's best to write that CHCOOH. Does that work out better? I don't really know. But yeah, and leave the ends open to show that it's going on and on and on. And I suppose I could put an N after one of the repeat units if I wanted. That's 2 marks. Let's look at the next question. Right, we need to do the condensation polymer, and it wants 2 repeat units. So I'm going to draw it here where it says addition polymer. Let me cross that out and write condensation polymer. Now, for the condensation polymer, the double bond bit is not going to open up and become saturated. We can just keep it as C2H3 to save scribbling it out properly. And all we want to do here is remove a water molecule and slap it all together. Let's go. Okay, so we're going to do NCH. Oh my days. I need to put that little C2H3. That's the double bond bit, the alkene bit coming off there. Then I've got the carboxylic acid. Now, this is going to join up with the amine on the other side. Hold on a minute. That's not an amide link, is it? I need my nitrogen to be bonded to the carbonyl group. What am I doing? There'd be no O there because the O would have come off with the water and the hydrogen on the amine on the left. Right, so it goes straight to a nitrogen. Okay, I got it. I've worked it out. You just got to make sure that you've removed H2O. And if you haven't at the end of it, if you've not removed 2 H2O, if you're joining 2 units together, you need to remove 2 H2O to form like one of these units with 2 monomers. 1 water molecule for each monomer, remember. So, yeah, 2 water molecules. That looks right. I think that's right. That's right. The OH has gone. Yep, the CH is there. The NH is at that end. The OH has gone on that end. The CH is, yeah. Okay, cool. I've displayed it like that. You could do it like they have with the C and the H together, or you could draw the H coming off the bottom like I did there. Anyway, that's 2 marks. There we go. That's the end of the queue. Going through an A-level chemistry practical techniques question. Let's get into it. Oil of wintergreen is a liquid used in medicine to relieve muscle pain. Compound H is a component in oil of wintergreen and can be synthesized from compound G, as shown below. The boiling point and density of compound H are stated. Here's compound G, here's compound H with a boiling point of 222 and a density of 1.174 G cm to the centimeter cube, sorry. A student prepares a sample of compound H by the method below. Reflux 8.97 grams of compound G for 30 minutes with an excess of methanol in the presence of a small amount of the sulfuric acid as a catalyst. Add an excess of aqueous sodium carbonate Na2CO3AQ. Two layers are obtained. Purify the impure compound H that forms from the resulting mixture. The student follows this method and obtains 5.32 grams of pure compound H. Why does the student use reflux? Pause. Have a go. Okay, reflux is used when we want to ensure that everything reacts completely, and also to prevent the evaporation of any of our product or any of our reactants, as we're dealing with volatile organic compounds here that often have boiling points where we might lose some through evaporation. Okay, so having reflux ensures that everything keeps condensing and falling back into the reaction mixture until it's all completely reacted and we don't lose any through evaporation. And that'll get us a mark. Right, now let's check out step two. In step two, sodium carbonate Na2CO3AQ removes the sulfuric acid catalyst and any unreacted compound G from the mixture. Write equations for the removal of sulfuric acid. So we want to write equations for the removal of the sulfuric acid and then a second equation for the removal of compound Okay, let's have a go at writing these two equations. I'm going to go through the answers, so you should pause if you don't want to see them yet. Na2CO3, that's our sodium carbonate, aqueous. We're going to add that to sulfuric acid. Of course, that's going to be aqueous. And that sulfuric acid is going to form sodium sulfate. So the sodium carbonate, one of its jobs is to neutralize excess acid that's left over. So it's going to form sodium sulfate, water, and carbon dioxide, and that's all going to balance beautifully. Now, if we take compound G and some of the sodium carbonate is going to react with compound G, and what's going to happen here is the carboxylic acid group of compound G is going to react with the sodium. So we're going to get that kind of like carboxylate ion that if you see what I'm saying there, that's sodium like methanoate or whatever the hell that is, that ion coming off there. And we're also going to get carbon dioxide and we're going to get water formed as well. Oh, forgot the hydroxide ion on the bottom of compound G. There it is. Right. Now we just need to balance. We're going to need two of everything. Well, we're going to need two of compound G, and because we're going to need two sodiums to react with it to form that O minus Na plus there. And we only need one of the sodium carbonate. Yep, that's all balanced. Lovely jubbly. Let's move on. Okay, part two. Another student suggests that adding aqueous sodium hydroxide would be more effective in removing the sulfuric acid than the sodium carbonate. Comment on whether the student's suggestion is an improvement for the preparation of compound H. Right, so when we want to remove that excess sulfuric acid catalyst that we reacted at the start here, would it be better to use sodium carbonate or sodium hydroxide? Well, carbonates form carbon dioxide and water, but the sodium hydroxide would actually do alkaline hydrolysis of an ester. Look, that's got an ester link there, and that ester link would get broken. So it would basically, you'd end up with a kind of carboxylate ion coming off the benzene there. So it would actually break the ester link. So I'm going to say no, I don't think it's suitable as you're going to hydrolyze that ester link. So yeah, no. Right, let's move on. Okay, we've got to calculate the percentage yield of compound H. It's worth 3 marks and it's to 3 significant figures. So calculate the percentage yield of compound H. Why don't you press pause on the video, get your calculator, pen, paper, have a go with this one. All right, I'm going to go through the answers. So we made 5.32 grams of compound H, but that isn't the theoretical maximum. So let's work out the yield by first of all working out the theoretical maximum of compound H. Now we've been told that we have 8.97 grams of compound G, and if we add up the MR for compound G, I've got C6H14 76, I've got 45 carboxylic acid group, 17 for that. That's a total of 138 is the MR for compound G. 8.97 grams divided by 138 gives me 0.065 moles. It's a one-to-one reaction with H, so I'm going to make 0.065 moles of H. So I now need to just rearrange the MR equation and do moles times the MR, which is 152 for H, and I'll get the maximum mass that I should make, which is 9.88 grams. My actual mass was 5.32, so 5.32 over 9.88 divided times 100. Sorry, I get 53.84. 3SF is 53.8. There we go. Okay, the final part to this question, describe how to purify the impure compound H. Compound, I can't speak properly. How do we purify pure compound H in step 2? Okay, so step 2, add an, yeah, right. We've got a sulfuric acid catalyst, which is removed by adding the sodium carbonate. But we've also got an excess of methanol that we use to with reflux to ensure that none of compound G was left, and it all became the ester H. So how do we get rid of the methanol? Well, we're going to the aqueous. We're going to get an aqueous layer. We're going to put in a separating funnel, get an aqueous layer, which is going to contain any excess methanol, water that's around from the solutions we've used. And that top layer will be aqueous in the separating funnel. So we can remove the top layer, tip it off, or we can use the tap to remove the organic layer, which is going to be the lower layer in the separating funnel. So we could tap off the organic layer. Um, of course, you can work out if you're confused because both layers are colorless and they look very similar, and you're trying to work out which layer is which, you can add a little bit of water, and the layer that increases in size will be the aqueous layer because water is going to add to the aqueous layer. So that will increase in size. So if you're unsure of which layer is which, add a couple of centimeter cubed of water and that layer will increase in size. So here's my separating funnel with a tap at the bottom, and you're going to be able to tap off that organic layer, which is going to essentially mainly be compound G, but you might have some other organic impurities in there. You should have, sorry, mainly compound H, which was our ester product. Our original reactant, compound G, should have all reacted under reflux. And we may have some methanol, which is obviously soluble in water, so will be in the aqueous layer. We can get rid of that. Then we're just really left with that organic layer, which will mainly be compound H, our product. Then we want to dry the organic layer because it will have some water with it. And we can do that using an anhydrous salt. And there's various different anhydrous salts you can use, calcium chloride or magnesium sulfate. So you probably get them up for saying anhydrous salt, but it's always good to mention one. So I'm going to say magnesium sulfate as my anhydrous salt I'm going to use here. And that's going to remove any H2O that is still in contact with the organic layer after you have used the separating funnel. Now, finally, I've got my impure compound H. I'm going to distill it. And I believe when we look at the stem of the question, what sticks in my head is the boiling point is 222. So I want to say distill compound H at 222 degrees. So we'll ensure that compound H evaporates and we condense it at 222. And that should secure the 4 marks. Don't forget sharing is caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you on the next vid. Welcome to Let's Get to the Marks. Going through an A-level chemistry question on NMR. So using organic analysis to find out the identity of an unknown compound. So what we've got here, we've been given the IR, we've been given the mass spectrum and the NMR spectrum of compound J. Determine the structure of compound J, show your reasoning 6 marks. What I'm going to do is I'm going to go back up and see if you can use the first 2 parts of the information to gather as much stuff as you can. Then we'll move on to the second part together. So what I want you to do is press pause on the video, see what you can use on this screen and what you can gather about compound J from this screen using the elemental analysis, the mass spectrum, and the IR spectrum of J. Let's go. All right, I'm going to go through the answers now. So you want to check out where they've given us the percentage by composition of each compound or element. So we've got 80.6 carbon, 7.46 hydrogen, and we've got 11.94 for oxygen. Now divide all of them by the AR, and that is going to give you 6.71, 7.46, and 0.746, sorry. Now what you want to do is divide by the smallest. By dividing by the smallest, we can try and get them into whole number ratios. We might need to multiply after that, but we'll see. So if we do this first one by 0.746, 6.71, we find out we've got 8.99 carbon. That basically means 9. The next one, we've got 10 hydrogen. And then the final one, we've got 1 oxygen. Okay, so we end up with just 1 oxygen, and that is the empirical formula. Now, time to find out if the molecular formula is the same as the empirical. And what you can do is you can add up the empirical formula. 9 times 12 is 108, plus 10 for the hydrogen, that's 118, plus 16 with the oxygen is 134. And if we check our relative intensity on the mass spec, or actually if we check the MZ ratio, the final peak here, the final substantial peak is at 134. So actually that gives us the MR of the largest fragment, or that's the N plus ion. So yes, we now know that the molecular formula is also 134. For instance, if the N plus peak had been 268, then we'd know we need to double that formula and it'd be C18H20O2, but that's not the case. Now we look along the IR and we find any distinct peaks, and there's one here at 1700 that's very, very common. You should get to recognize this. This is so common on the exam board. What I got to do now is find the data book and try and show you what that is. Anyway, you can't see my data book. For some reason, it's not popped up. But it is 1700, between about 1620 and 1800 is the carbonyl bond. So what we know from this is that we've got the COO bond found in aldehydes and ketones. So we have that from that 1700. So that's the information we've got. Let's consolidate that information here. And then I'm going to get you to pause the video and see if you can break down the hard bit, the bit everyone's interested in, the NMR. So the empirical formula and molecular formula is C9H10O. Or yeah, I should write that because they don't come out well in numbers. So C9H10O. What does that mean? That means that we know when we're going through and piecing together the NMR, we've only got one oxygen atom. So we need to be careful with that. Also, the one oxygen is in the COO bond. So we know we've just got a carbonyl bond. We can't have a carboxylic acid because that would require two O's. We can't have an ester, that would require two O's. So we kind of know that stuff from the IR. Right, why don't you pause the video, see if you can analyze the NMR data, and then unpause, and I'll go through the explanation. So what I want you to see here, I've circled, these are all the integration trace or relative peaks, and they all add up to 10, and we've got 10 hydrogens. So they basically, they're equivalent to the amount of hydrogen in that environment. So let's look at that first environment I've circled at 1.6 ppm chemical shift. The hydrogen in the environment has a relative peak of 3. This means that it must have 3 hydrogens. That can only be a CH3 group, right? 3 hydrogens, it's got to be a CH3 group. So it's also got a splitting pattern. We've got a doublet. This means that the carbon adjacent to the CH3 has 1 hydrogen attached. So now we know we have a methyl group with a CH attached because it gave off a doublet. It tells you about the next environment, the adjacent carbon's hydrogen environment. So essentially we know we've got a CH3 attached to a CH. Now we're going to go here. This one people find a little bit difficult. This is called a quintet. It's basically got 5 mini peaks. It's kind of like they're in that ratio, 2 tiny ones, then 2 ones, then 1 big one in the middle. And it's between 3.5 and 4 ppm. And this has told me it has a relative peak area of 1, which means that it is a carbon with 1 hydrogen attached. It could be that CH we've got there in the middle next to the CH3. It could be that. And it tells us that it's a quintet. It tells us that it has 4 H's attached. So on adjacent carbons, remember you do the N plus, the H plus, or N plus 1 rule, whatever it is, minus 1 rule, whatever. So quintet tells you there's 4 hydrogens attached on adjacent carbons. Now, 4 hydrogens cannot be on 1 carbon. So it means that it's probably this CH I'm circling here, and it's telling us that it's got that methyl group, but then another CH attached on the other side. We don't know the other bonds attached to that carbon yet, or even the middle carbon. So we're going to work on that next. So we're going to get off the quintet. But essentially, the quintet is possibly telling us, it's this hydrogen here I've circled over here, it's possibly telling us that it has 4 hydrogens in the environments around it, okay? But it itself has an integration trace or relative peak of 1, so it only has 1 hydrogen. Moving on, between 7 and 8 ppm, we have a relative peak area, sometimes called an integration trace, of 5, or a ratio of 5. And due to the fact that we don't need to use a ratio here because we've got 10 total relative peak area, we know that this has 5 hydrogens. So what kind of environment could have 5 hydrogens? Well, if we check out on our data sheet between 6 ppm and 8 ppm, you'll find that that is going to be like a benzene ring, an aromatic ring. So that means we're going to have a C6H5. So we've got this kind of benzene ring thing going on here. Okay, and what this is, it's also a singlet. kind of looks like a doublet with a baby peak there, but it's not. It's a singlet. And the singlet means there is a carbon atom on this ring with no hydrogens attached. So I'm going to draw it out. Look, imagine we've got this benzene ring here, 5 hydrogens. That gives us the 5 relative peak. Let's circle this hydrogen, pretend it's that one that's given us the 5. It also has given us a singlet telling us that the next carbon next to it has no hydrogen attached. And that would make sense. I've circled it in green. That would be why it is a singlet, because this carbon is probably going to be attached to my little group of CH3CHCH that we've already established. So let's attach that there and then count it up and subtract it from our C9H10, right? So we can go, oh, look, yeah, I've got 10 carbons. That makes sense. And then we count up the hydrogens and we go, oh, yes, it makes sense. We've got 10 hydrogen. The only thing we don't know is where is the oxygen? Is it hanging off a benzene ring? Is it coming off of one of these carbons? So we go to here at 9 ppm. I mean, we can probably guess where the oxygen is right now, right? Considering we need a carbonyl group. But at 9 ppm, we have a doublet, which means that it is a hydrogen in an environment where adjacent to it is a carbon with 1H. And the fact that it has a relative peak of 1 tells us that it has 1H. Again, this is looking like our 2CH groups. Look at our 2CH groups. It's telling us that one of them is next to the other. We know which one it is. And also, if we look up 9 ppm on the chemical shift in our data book, we're going to find that it is the carbonyl bond. So we're going to change this now and piece together the whole thing. So really and truly, this all makes perfect sense. It's telling us we've got this carbonyl group and it has 1 hydrogen in its environment. So it's like an aldehyde, right? A hydrogen and a carbonyl. And it says, hey, I've given you a doublet. That means I'm attached to a carbon with 1 hydrogen. And that makes sense. So it should be that CHO is attached to a CH, then the CH3, and then on the left of them is the benzene ring. So look here, there we go. Let's piece the whole thing together. And it's going to get you all of the fat 6 marks. And even if you have trouble solving the final formula, remember you can get tons of the marks just by stating what the relative peak or integration trace tells you about the number of hydrogens, and then about what the splitting pattern tells you about adjacent carbons and their number of hydrogens. Anyway, that's the end of that one. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.